Lesson 21, Perpendicular and Angle Bisectors. The objectives of the lesson are to prove and apply theorems about perpendicular bisectors, prove and apply theorems about angle bisectors. Your vocabulary words are equidistant and locus. Let's start with a definition of equidistant. When a point is the same distance from two or more objects, the point is said to be equidistant from the objects. Triangle congruence theorems can be used to prove theorems about equidistant points. One of the equidistant points that we are very familiar with would be the midpoint. It is in the middle of the segment and it is in between the two endpoints. It's equidistant. We have two new theorems. 511, the perpendicular bisector theorem, states that if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So if you look at the picture under hypothesis, and you see that we have the blue lines, and if we just look at the blue lines AB and line L that intersects AB, we're told that L is perpendicular to AB and that AY or YA and YB are congruent. What the perpendicular bisector says that if a point is on that bisector to a segment anywhere on line L, then it is equidistant from the two endpoints of the segment. That is, it is equidistant from A and B. So XA will equal XB. 512 is the converse of the perpendicular bisector theorem. It simply states the opposite. If a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So in this case, we're given that we have an isosceles triangle. We have a perpendicular bisector, but we aren't sure if it's perpendicular. However, the two sides are the same, and point X is on line L. That means that XA and XB are equal, which tells us that we have a perpendicular bisector, and XY is perpendicular to AB, and that tells us that YA and YB are equal or congruent. A locus is a set of points that satisfies a given condition. The perpendicular bisector of a segment can be defined as the locus of points in a plane that are equidistant from the endpoints of the segment. So every single point on the perpendicular bisector is equidistant from the endpoints of a segment. That means that it is a infinite set of points, as there are infinitely many points on a line, and this would be the locus of the points that satisfy the condition that they must be equidistant from the endpoints. Let's look at an example. If we want to find the measure of MN, and we are given ML is the base of this triangle, and MP and LP are congruent, and line P is perpendicular to ML. Since we know that those two segments are the same and we have a perpendicular bisector, then that means that MN must be equal to LN. This is by the perpendicular bisector theorem. And then if we just substitute in 2.6 for LN, we have our answer. MN equals 2.6. Example 1b, we have a sideways triangle, and we want to find the measure of BC. And we see that BC is bisected by AD, line AD, and that BA and CA are the same length. That tells us then that DB and DC are also congruent. Since they are congruent, then that means that BC is equal to 2 times CD. Then all we have to do is substitute in the 12 for CD, and we get that BC is 24. This time we want to find the measure of TU. We have TV is intersected by UW, and it is perpendicular, and TW and VW are equal. So that must mean then that U is equidistant from T and V. So 3x plus 9 will equal 7x minus 17. If we set this up as an equation and solve, we subtract the 3x from both sides. We're going to add 17 to both sides and then divide by 4. We get that x equals 6.5. But we weren't really looking for x, we wanted to find the length of TU. So if we plug 6.5 in place of x, we end up that TU is equal to 28.5. We have two other theorems, 513 and 514. And these are the angle bisector theorem and the converse of the angle bisector theorem. If a point is on the bisector of an angle, then it is equidistant from the sides of the angle. So, if we are given that APC is congruent to BPC, and we see these little red lines here, then PC is the angle bisector, and C is going to be equidistant from A and B. So AC equals BC. The converse of this theorem tells me that if AC and BC are equal, then my two angles are going to be congruent. Based on these theorems, an angle bisector can be defined as the locus of all points in the interior of the angle that are equidistant from the sides of the angle. Let's look at an example. If we want to find the measure of BC, we look at our picture and we can see already that BAC and DAC are congruent. We have perpendicular lines here and here. So BC is equal to DC. This is from the angle bisector theorem. BC equals 7.2, and all we did was substitute in 7.2 for DC. If we want to find the measure here, and the measure of EFH, so this side here, and given that the measure of EFG, the entire angle, is 50 degrees, since EH is equal to GH and EH is perpendicular to FE, and we have GH is perpendicular to FG, FH is your angle bisector, and that's by the converse of the angle bisector theorem. So the measure of EFH is half the measure of EFG. This is the definition of angle bisector. So if we plug in 50 degrees for EFG, then we get that the measure of EFH is 25 degrees. In example 2C, We want to find the measure of MLK, or MKL. So MKL, that would be 2A plus 26 degrees. Since JM is equal to LM, and KJ is perpendicular to JM, and KL is perpendicular to LM, we know that KM is the bisector of the angle. This is by the converse of the angle bisector theorem. That means that the measure of MKL equals the measure of JKM. So, if we substitute in the values that were given, and we solve for A, we get that A equals 6. To find the measure of MKL, we substitute in 6 in place of A in the expression for K. 2 times 6 plus 26 equals 38. Let's look at another example. Example 3 is an application. S is equidistant from each pair of suspension lines. What can you conclude about QS? So the suspension lines, we have P and R here, and S is equidistant from these two lines. So QS would be the angle bisector. For example 4, we want to write an equation in point-slope form for the perpendicular bisector of a segment with endpoints C, 6, -5, and D, 10, 1. This is a multi-step problem. For step 1, we want to graph CD. So we put in the points. We have 6, -5, and we have 10, 1. The perpendicular bisector of CD is perpendicular to CD at its midpoint. So step 2, we need to find the midpoint of CD. We know that this is x1 plus x2 divided by 2, and y1 plus y2 divided by 2. So the midpoint of CD is 6 plus 10 divided by 2, and -5 plus 1 divided by 2, or the point 8, -2, right here. Then we need to find the slope of the perpendicular bisector. Slope is y2 minus y1 over x2 minus x1. The slope of CD would be 1 minus -5 over 10 minus 6, which would give me 6 over 4, or 3/2. Since the slope of the perpendicular lines are opposite reciprocals, the slope of the perpendicular bisector is -2/3. We take the 3/2, we flip it over and make it negative. Step 4, we're going to use the point-slope form to write an equation. The perpendicular bisector of CD has slope -2/3 and passes through 8, -2. So y minus y1 equals m times x minus x1. This is the point-slope form. So y plus 2 equals -2/3 times x minus 8. We're substituting in -2 for y, -2/3 for m, and 8 for x1. This would be our line. Now you try. and 3 others. Our next lesson will be 5.2 and 5.3, bisectors in triangles, medians and altitudes of triangles. Have a nice evening.